Integration by substitution. When we looked at integration by inspection, and then we delved a little deeper and looked behind the scenes at what's actually going on, we ended up using substitution. So we have seen a version of this already. What we're going to look at today is how we can apply the same kind of technique to a much wider range of situations. As we saw before, if there's a particular annoying bit of the integral which we can replace with a new variable, typically we use u, then often the entire integral can be reduced to a simpler version. And once we've got a simpler version, we can integrate it directly and then convert back at the end so that everything's in terms of x if we need it to be. We're going to look today at a few variations on the integrals we saw before to start with, to see what's similar and what's different. And then we'll start to get a sense of the more varied types of problems that integration by substitution can solve for us. So I'd like you to begin by having a go at these three questions. Two of them should feel relatively familiar if you're comfortable with integration by inspection, and I'd encourage you to use whatever method you're most familiar with when you're dealing with those. But one of them will seem a bit different, and I want you not just to be stuck on it, but to think about what makes it different. So pause, have a go at those. When you're ready, we'll continue. Let's start with this first one. We have 3x squared minus 1 inside a bracket raised to the power 4. That means we're going to want to deal with the 3x squared minus 1. Fortunately, the derivative of 3x squared minus 1 appears as a factor within the integral. So that is going to work quite nicely. We make u equal to 3x squared minus 1. And then the very next step is always to identify a link between du and dx. So if we can just differentiate with respect to x, we get du by dx equals, in this case, 6x. And because x appears as a factor within the integral, the 6x that we get when we differentiate and find du by dx will end up cancelling out. We can see when we rearrange, we get 1 over 6x times du. So it'll cancel nicely. The original integral, which is functions of x dx, is being turned into a new integral involving functions of u and du. The bit that isn't quite sorted yet is the x. There's an x that was still in the original integral, but luckily there's also an x that appears in the derivative term. The du and the dx get replaced, swapped out, and what's left behind is a 1 over 6x. So those two bits actually sort each other out. They cancel out, and we're left with an integral which is only in terms of u. As soon as you've got that, the following process is relatively straightforward. U to the 4 becomes u to the 5 over 5, and the 1 over 6 term that was there already is still there. We add a constant, and at the very end, we just replace u with the thing that u was defined to be at the beginning, 3x squared minus 1. Let's look at the next one. This has 3x minus 1 inside a bracket raised to the power 4, and what makes this one nice is that the derivative of that awkward bit, the derivative of 3x minus 1, is just a constant. So this, in some sense, is even simpler than the inspection cases that we looked at last time. If u equals 3x minus 1, then du by dx is just 3. So we can replace dx with a third du. And if we do that, the entire integral sorts itself out straight away. The 3x minus 1, of course, gets replaced with u, and dx is replaced with a third du. Now we have an integral which doesn't involve any x's at all, so we can integrate directly. U to the 4 becomes u to the 5 over 5 once more, and we end up with 3x minus 1 to the power 5 all over 15. This third one is where things start to get a little bit different. It doesn't seem on the surface that much different to the previous two. It's got a 3x minus 1 in a bracket to a 4, just like the second one, and it's got an x in front, just like the first one. But those two things don't necessarily play as nicely together as you might think. If we start with the logical substitution, 3x minus 1, we can find the same connection between du and dx. And let's see what happens when we plug it into the integral, see what's left behind. We can get rid of that 3x minus 1, because that will just be u, and we can get rid of dx, because that will just be a third du. But we still have an x term right at the front. And that's what makes this type of integral a little bit different to the inspection cases. These ones are somewhat harder to do just in your head as a reverse differentiation process. Certainly I wouldn't feel comfortable diving into that and expecting anything like the correct result without going back and checking my work over and over again. So I'd find it much easier to apply this formal substitution approach. But when we get to here, we don't need to completely give up. The x that you see there needs to be dealt with. In other words, we need to find a way of getting rid of it in preference for a function of u. Well, we do actually have a connection between u and x. If you look closely, you'll find that we identify u as a function of x right at the very beginning. We chose to let u equal 3x minus 1. So we do something a little bit sneaky. We say, well, if we know that u is 3x minus 1, then x must be u plus 1 all over 3. So we can get rid of it, not completely by cancelling it out and making it disappear, like happened in the previous case, but we can get rid of it by replacing it with a function of u. Typically, this gives us something a little less straightforward than we've had before, but crucially, everything involves u. There is nothing in there with a trace of x. We have u plus 1 over 3 multiplied by u to the power 4 multiplied by a third, which is just a constant, and then finally a du at the end. So we can integrate the entire thing with respect to u. In order to integrate something like this, you might remember from your year 1 content that you need to first multiply out the brackets. And I'm also going to pull out those 2 over 3s that we've got going on. So we have 1 over 9 multiplied by the integral of u plus 1 times u to the 4 with respect to u. And if we expand out that bracket, we get this, and suddenly this integral is looking a little more friendly. U to the 5 becomes u to the 6 over 6. U to the 4 becomes u to the 5 over 5. We still have that factor of 1/9 out in front. We always remember to put an arbitrary constant at the end because there's an entire family of functions that satisfy this same integral. And at the very end, this is where it starts to look messy again. You have to replace u with the function of x which u represents. So we're coming back to that bit circled in green. U is equal to 3x minus 1. So wherever u appears, we're going to write 3x minus 1. Hopefully that doesn't feel too different to the process we've done before. The underlying mathematics is the same. The only sneaky extra bit is the bit I've indicated with the purple arrow. This is where any additional functions need to be dealt with as well. And provided you can find a rearrangement, and provided the resulting integral is not too complicated, then this method can work wonders. It's not always obvious when an integral can be effectively evaluated using substitution. There are a few different types of substitution that you'll come across, and it's useful to see some examples so that you won't be taken by surprise when you attempt to use this technique and something changes and you're not quite sure how to adapt it. It can be rather challenging, especially when you're new to it, to recognize what's similar and what's different from one question to the next. But the underlying fundamental idea behind substitution is that it's a change of variable. Substitution does not claim to do the integration for you. It's an approach, a process you can use to convert your integral problem into a different integral problem. This is a common theme. You'll see it again with integration by parts. The idea is you start with an integral, in this case in terms of x, with respect to x, and you perform a nifty change of variable and you make it a function of u with respect to u. Integration by parts will do a similar kind of thing, taking one integral and allowing you to rewrite it in terms of another integral, and the hope is that you're able to deal with the new integral that you've been given. Substitution will work like this. If you find a good substitution, you can rewrite your integral in a way that is easier to evaluate. There are a number of different types of question, as I said, that use substitution. So we're going to start by taking a look at one particular type, and we'll see what's similar and what's different between them. Let's have a look at this. Sine of 2x over 2 minus cos x. And just like when you're solving a tricky equation, a good starting point is to ask yourself what makes this integral difficult. If there was one particular bit that you could change in order to make it easier, what would you change? And if you can identify that, you've recognized which the sticking point is, And that's the bit you want to try to use substitution to deal with for you. So I'd encourage you to pause at this point and just jot down anything that comes to mind about what makes this integral difficult, any useful identities you think might come in handy, and then when you're ready and maybe you've got some ideas about how to substitute, jot them down, and when you want to see a bit more of the example, then unpause and continue. So one of the things you might have written down is the identity for sine 2x. The double angle formulae may or may not come in handy in this particular question. It's maybe too early to tell for you at this point, but knowing what they are is definitely going to be helpful in identifying whether a particular substitution might come in handy. So if you don't know them off by heart, that's not a huge problem, as long as you know them sufficiently to recognize when you might find them useful, and then to go to the formula book, look up the sine a plus or minus b and cos a plus or minus b formulae, and derive them directly from there. Sine of 2x is 2 sine x cos x. So I'm already thinking, if the denominator was just cos x, things would cancel very nicely. The denominator isn't. It's something which is similar to cos x. It's even something which will differentiate to something very similar to cos x. It's just not quite the same. That's a good indication that a substitution there might pay dividends. So let's see what happens. If we set u equal to 2 minus cos x, the pesky awkward bit of this integration, it's a fraction, there's a nasty denominator. Let's see if we can deal with it. Even if nothing else happens, at least we'll be left with a single term in the denominator, and we might be able to divide through by u at the end and make ourselves a nicer integral. But we notice that du by dx equals sine x, which isn't immediately obvious, but it is a factor of the integral. Sine 2x is not the same as sine x, but it is the same as 2 times sine x times cos x. So if we're careful with our trig identity use, we can recognize when a substitution is about to play nicely. Let's see what happens when we put all of this in. So for now, I just write it in exactly what I've got. The denominator disappears. Dx gets replaced with 1 over sine x times du. That's just by rearranging the du by dx equals sine x expression, identity, equation. And then we can start making use of the double angle formulae. Sine 2x becomes 2 sine x cos x. And when we divide by sine, you can see what's going to happen here. We'll have some nice cancelling out, and we end up with something a bit more elegant. Now this last bit is a little bit like the last example we looked at. Yes, we get 2 lots of cos x over u du, but that doesn't completely solve the problem. We still have cos x. But it's not that big of a problem, because if you recall, u and cos x are very closely related. They add together to give 2. U is equal to 2 minus cos x. So cos x is equal to 2 minus u. And that means we can just replace it with the appropriate function of u. And it gives us something which is relatively nice. We can, as hoped, divide through by u. In other words, each term of the numerator can be divided separately by the single term denominator. 2 times 2 over u and 2 times negative u over u. And this is how it finishes. So we have 4 over u minus 2. And then when we integrate, 4 over u becomes 4 lots of ln u, because 1 over u integrates to ln u. And 2 becomes 2u. And at the very end, we just replace u with 2 minus cos x. So here's a useful checklist for you. Whenever you do a substitution, generally speaking, these are the steps you're going to be following. First, you select a substitution. The most common sorts will be u in terms of x, or possibly x in terms of u, but there are a couple of other variations as well. Essentially a connection between the variable you have, which is normally x, and the variable you're introducing, which is normally u. The next thing to do is find a link between the derivative bits, the du and the dx, the infinitesimals. And we can do that by differentiating the thing that links u and x together. So if we have u equals something in terms of x, like we did in this case, then we differentiate with respect to x and we get du by dx equals something. Now the result may involve x and or u as well as constants. but that's not necessarily a problem in and of itself, as we will see. Once we've got the connection between du and dx, then we replace dx with something involving du. That effectively deals with the dx part of the issue. And then we simplify. You simplify as much as possible. That might be all you need to do. At that point, anything involving x might completely disappear. But if not, you might need to replace any remaining functions of x with functions of u by rearranging your original equation that you used to make the substitution. Now, if that gives you something even more complicated and horrible than you had at the beginning, it's possible that you've chosen a substitution that isn't very helpful. And that can happen, especially when you're first learning about this topic. It's not immediately obvious what the most sensible substitution would be. It's a creative problem-solving process, and you may well need to try a few different routes before you find the one that gets you through to the solution. Once you've managed to find an appropriate substitution and things cancel out and leave you with a relatively nice-looking integral, like ours, 4 over u minus 2, it's a delight because every single bit of it is something we can integrate directly in a single line. Once you've got that, you perform the integration, don't forget the plus c, and then finally at the very end, you go back and you replace every instance of u with the appropriate function of x. There's a few questions now you can have a go at from the textbook, exercise 11e. If you tried these ones using the techniques that we talked about, hopefully you'll be able to see what's similar about them, what's a little bit different, start to build a bit of confidence. In some cases, you'll be told what substitution to do, and in other cases, you'll be left to choose the most appropriate thing to substitute for. The next example I want to look at involves definite integration. In other words, integration between two limits. There are a couple of differences between indefinite integration, say the integral of 3x squared dx, and definite integration, the integral of 3x squared dx between 3 and 4, let's say. One of the issues is that the limits are not explicitly stated as limits for x, and yet they are limits for x. This is the main thing that trips people up with this, because your focus, quite rightly, is on the complexities of whatever the function is inside the integral and ensuring that you've effectively dealt with the dx when you're converting to something involving du, and it's very easy to forget that you've got limits that involve x. One of the easiest ways to deal with this is to change them from implicit limits to explicit limits. In other words, you state that instead of the integral from 3 to 4, you write it as the integral from x equals 3 to x equals 4. And as long as you consciously do that at each stage, then you will know and remember when you've done it, and you'll easily pick up when you've forgotten to do it. So in general, the thing to remember is when you're dealing with any sort of integration by substitution, you got to treat it like a breakup. You want to get rid of any trace of the x. Eventually, you should have something which is all about u. That's the general idea. So the function itself should be a function of u. The dx at the end should be a du. And even any limits that you have, which are hidden versions of x, you've got x equals something and x equals something else, those also need to be converted using the same rule that links u and x that you come up with at the beginning. So it's not a difficult thing to do. It's just an easy one to forget to do. So let's see what it looks like. If you're given an integral that looks like this, the first thing you should do at the very beginning, if you're thinking of using substitution at all, is to rewrite it so it looks more like this. Color coding optional. But the fact that you've got x equals 2 and x equals 5 now highlights for you, every time you read through it, you're essentially looking for those bits that stand out. They should jump out at you like a red flag. There's something involving x. I need to deal with that and get rid of it so I can move on. Let's next look at what the substitution is going to be. If you want to pause at this point and have a quick think, or jot down what you think an appropriate substitution might be and why, then I'd recommend you do that. See if you guess correctly. What we're going to do is deal with the bit under the square root. We don't like the fact that we have the square root of e to the x plus 1, but it turns out if we set that to be our new variable, u equals e to the x plus 1, then its derivative, which is e to the x, does appear as a factor of the integral. It's not the only other thing. We've got e to the 2x, so e to the x only accounts for some of that, but it does account for some of it, so it will at least combine relatively nicely with what we've already got. Let's see what happens when we put it in. So we can replace dx with 1 over e to the x du, or e to the minus x du if you prefer. We can get rid of everything under the square root sign. That becomes u. And then you'll notice I've still not dealt with the limits. I've left them as x equals 2 and x equals 5, as a reminder to myself that I've not yet sorted them out and that I need to at some point soon. The next thing I'm going to do is simplify. We can do that fairly easily. We're dealing with the e to the 2x and the e to the minus x. They can combine. But then at this point, before I start worrying too much about the e to the x, of course the order you do these things in doesn't really matter, but I'm going to hit those limits next. I'm going to say I've got x equals 2 and x equals 5. These are easy things to fix. Let's fix those now and then worry about the final piece, the e to the x, and deal with that bit. So here's how you convert the limits. We focus on the fact that we already have a connection between u and x. The connection is u is equal to e to the x plus 1. So if x equals 2, then u will equal e to the 2 plus 1. And the same thing happens with 5. If x is 5, just substitute 5 into our expression for u, e to the 5 plus 1. So it might be a little tedious to write it out, but it's a good idea to include those limits, again explicitly as limits for u in our integral. The other thing that we can do at this point, because it's actually pretty quick and easy, is to recognize that that link we've got between u and x, that will allow us to easily replace e to the x with something involving u. If u is e to the x plus 1, then e to the x is just u minus 1. So our integral can now be converted to this thing, which has no trace of the x anymore. All we're dealing with is a function of u, a du, and two limits which are limits in terms of u. You can think of this a little bit like a graph that's been transformed in some way. If you move a graph to the right and then you take the integral and you want any kind of connection between the integral you're taking for your new graph and the old graph, the limits also need to move to the right. If you think about how much of the quadratic y equals 10 minus x squared is above the axis, well, if you shift that so it becomes 10 minus x have 3 in a bracket squared, so you've shifted it to the left 3 places, you're going to need to recalculate where those crossing points are. They will have moved to the left 3 places just the same as the rest of it. So that's essentially what these limits do for us. We don't need to know or understand or even have a vague picture in our heads of what the geometrical transformation is that's taken place. That's all taken into account for us when we replace dx by something involving du. But it's also taken into account by the change in limits. If the points that we're integrating between have changed, then they will change according to exactly that same rule that we've used to do the substitution. So now finally, we have an integral we can deal with. Needs a little more work, but not much. We can expand out those brackets. So u times the square root of u, we can think of it as u to the 1 times u to the half. So we get u to the power of 1 1/2. I'd advise you, just a minor point, but if you're still writing u to the power of 1.5 or even worse, u to the power of 1 1/2 as a mixed number, you should start to get into the habit of writing u to the power of 3 over 2. Because when it comes to things like integrating, you want to be able to quickly and easily multiply or divide by that power. And it's a lot easier to do if it's written as a top-heavy fraction rather than some kind of mixture or decimal. So now we integrate, we increase the power by 1, so 3 over 2 becomes 5 over 2, and we divide by the new power. You can write it as u to the 5 over 2 over 5 over 2 if you like, but be careful that you write it clearly if you do that. The alternative is that instead of dividing by 5 over 2, you multiply by 2 over 5. In other words, the reciprocal. So that's what I've done here. We've got u to the 5 over 2 multiplied by 2 over 5, and then u to the 3 over 2 multiplied by 2 over 3. And then finally, we substitute in the limits. The nice thing about this approach is that we don't need to go back and turn everything back into a function of x. That was the other alternative. We could have kept the limits in terms of x all the way through, and at the end, replaced u to the 5 over 2 times 2/5 with e to the x add 1 to the 5 over 2 times 2/5. Comes out exactly the same, but generally speaking, this approach is a little more efficient. As long as you know that everything you're dealing with here is in the same variable, it will give the same result. So we substitute the numbers in, and we get this delightful beast. Notice there's no plus c because we're doing definite integration. So although an integral evaluated without any limits has a constant, an uncertainty associated with it, so there's a family of functions that satisfy that result, if you integrate between two limits, it takes away exactly the same uncertainty constant that you would have had in the first place. Think of it as you don't know how much money I have in my wallet, and you still don't know how much money I have in my wallet after I pay you £10, but you do know for certain what the difference is between the two amounts of money, because you watched me pay you £10 and there's now exactly £10 less in my wallet. That's what happens when you substitute these numbers in. So we're not finding the value of this thing at a particular number. It's more like we're finding the difference between the two values of the integral. And that is something that we can be sure of. I wouldn't recommend you try simplifying this any further. You could pull out a factor of 2/5, but it's not necessarily going to give you any greater insights. If you have 2/5 of one thing, take away 2/3 of another thing, it doesn't necessarily make life any easier. It's certainly not going to be possible to get a nice, simple result if you try expanding brackets. They all involve powers of a half, so that's just going to make your life more difficult. This, in its current form, is, as far as I can tell, the simplest way of writing the exact answer. Now there's a couple more questions you can have a go at. Questions 4 and 8. They will involve integration by substitution again, but this time you'll have limits that you need to put in. So make sure you are conscious and you're aware of at which point your limits change from being limits in terms of x to limits in terms of u. Let's just look back briefly at an earlier question, just to demonstrate what happens when you apply a substitution if you were then going to put limits in. You can see the original curve, sine 2x over 2 minus cos x, shown in red. It's got that characteristic trigonometric feel to it, although it does look a little weirder than a standard trig graph. And then the new transformed version, 4 over x minus 2, or 4 over u minus 2. That's been drawn on the same set of axes, so you can compare them directly. The reciprocal graph has no trace of the sinusoidal shape of the original curve, but that doesn't matter because it's been taken into account by the way the limits change as the original limits are changed. So if you think about what kind of results you're going to get for the integral of that red graph, as you make the limits further and further apart, it doesn't balloon up as big as you like or go as massively negative as you like. All that happens is that it oscillates back and forth. If you have lots of the negative bits, it'll be a larger negative number, but the further you go, the more positive bits and negative bits you encompass. And they end up kind of cancelling each other out most of the time. You can see here that the limits in the blue graph will vary back and forth as the limits for the original red graph get changed. And that kind of makes sense because although the transformed function is this crazy reciprocal graph that presumably has an asymptote at x equals 0 or u equals 0 rather, that doesn't actually matter in this case because the limits are 2 minus cos x, which means the limits are restricted. They follow the range 2 minus minus 1 and 2 minus 1. Cos x varies between 1 and minus 1. Therefore, u will vary between 3 and 1. So the highest that will ever go on that blue graph is 3, and the lowest we ever go is 1. And that's why those limits are showing up the way that they are. The curve itself may look very, very different. If we've done a really effective substitution, that curve may look really straightforward. It might even be a straight line, sometimes even a horizontal line. But the limits will have something sophisticated going on that take into account the complexities of the original curve so that the integrals always match exactly. These next examples are designed to show you how we can deal with a substitution where perhaps instead of the more standard u equals something in terms of x, we might have u squared equals some function of x, or even something a little more strange looking, any other function of u. In general, the idea is we still need a connection between dx and du, so we still need to differentiate, but it's not necessarily going to be essential to write u explicitly in terms of x. An implicit form would be just as useful for us, depending on the situation, and may often be even easier. If you have u squared equals something, you can just use implicit differentiation. It'll still give you a connection between dx and du. And just because u and x may both appear in the final result doesn't necessarily cause a problem. We'll see what happens when we try an example. E to the 2x times the square root of e to the x plus 1 is one we saw before. Last time we used u equals e to the x plus 1. I want to go through it this time with u squared so you can see the differences. You wouldn't necessarily have a particularly strong preference one way or the other. Sometimes you'll be given the substitution, and if they give you it in this form, it makes sense to keep it in this form and use the one they've given you. That's what they're testing you on after all. So if u squared equals e to the x plus 1, then we can differentiate implicitly. U squared becomes 2u du by dx. So we differentiate u squared with respect to u to get 2u, and then we multiply by du by dx so that the final result is something which is a derivative with respect to x. And on the right hand side, e to the x plus 1 differentiates to e to the x when we differentiate with respect to x. That means we can do a bit of a rearrangement. We have dx equals 2u over e to the x du. And when we substitute that in, and we substitute u squared in place of e to the x plus 1, one of the nice side effects is that we have the square root of u squared. In other words, we have u. And other things will cancel nicely at this point. So although we still have that e to the x, we've got u multiplied by 2u, and the e to the x term can be replaced with u squared minus 1. As a result, instead of what we got the last time we did this particular integral, which involved all sorts of awkward fractional powers, we've got something involving nice whole number powers of u, 2u to the 4 minus 2u squared. When we integrate, we end up with 2u to the 5 over 5 and 2u cubed over 3. And the last step is the first time you'll see this as being equivalent to the one we did before. Because when we substitute back, we have to replace u with whatever u is equal to. This is the only point in the whole proceedings where you need u in terms of x, rather than just u squared in terms of x. So we'll need that e to the x plus 1 to the power of a half, essentially. That's what u will be. And when you raise that to the power of 5, you get e to the x plus 1 to the power of 5 over 2. The same sort of thing for the next bracket. Here's another example to show you another time when it might be easier to use a different format. This has a cube root of something. And although we can deal with u to the power of a third, and usually that will work just fine, you will often find it more efficient if you use a slightly different form. So u cubed equals 4x squared minus 7 will still allow you to find a derivative of the form that appears in our integral, that 8x that we get when we differentiate both sides. Well, we've got a 5x in the integral, so x is a factor of the original integral. The 3u squared, well, we're happy with that. We can work with that, factor it into our integral, it's not going to be a problem. So dx is equal to 3u squared over 8x times du, and therefore the integral, we can get rid of the cube root of 4x squared minus 7, because that's exactly equal to u, it's the cube root of u cubed, and then instead of dx, we have 3u squared over 8x du. Now there's a couple of things that can cancel out. The x will disappear from there and there. And the 5/8 and the 3, well, they could be combined a little bit and made a bit more efficient. And then we have u times u squared. So the final result will look something more like 15/8 u cubed, which we can integrate pretty easily. 15/8 we can hang on to, and then u cubed becomes u to the 4/4. And then when we combine with the 15/8, we end up with 15u to the 4/32. At the very end, we just substitute back that 4x squared minus 7 to the power of a third, because u cubed equals 4x squared minus 7. So we need the cube root of that if we want u itself. Simplest way is to put it directly in there and have a power of 4/3. And we're done. Here's a few more questions that you can try on this. The last couple of parts of question 1 involve substitution like this, and questions 5 and 6 from the book. The last example I want to examine is what happens when the substitution we're offered is not u equals something in terms of x, or even u squared equals something in terms of x, but it's been flipped around entirely and you've got x equals something in terms of u. Now this may feel like a very different situation, but under the hood it's exactly the same process. We can still take advantage of differentiation to find a connection between du and dx. So we don't necessarily have to rewrite it. You don't have to rearrange everything so it says u equals. You can use implicit differentiation if it's helpful. We can also, remember, we can find dx by du instead of du by dx, because that gives us just the same valuable connection between dx and du. There's no choosing between them, really. Either is as good as the other. We'll see what that looks like with the next example. But also, the example I'm going to show you indicates why you might find it useful to use a substitution of this kind in the first place. It just seems like it's additional complication unless you can see the value of it. Take a look at this integration. The square root of 1 minus x squared. Now, you may not see immediately why this is a trigonometric substitution, but it is. There is something about this which is very strongly, deeply connected to trigonometry. There's no sines, coses, or tans in there. There's no sec, cosec, or cot. And yet somehow there's something about this that feels trigonometric. Can you see what it is? Well, if I asked you to write sine theta in terms of cos theta, you might end up using a very similar structure to this. We know the link between sine squared theta and cos squared theta. Sine squared theta is 1 minus cos squared theta. So that means sine of theta must be the square root of 1 minus cos squared theta. The square root of 1 minus something squared. That's the underlying structure we're going to be taking advantage of here. I should just reassure you, this type of integral is not the sort of thing that you'll be expected to guess the substitution for all on your own in A-level maths. You won't be expected to look at this and suddenly say, oh, I think it's a trig substitution of this form. Don't worry about that. What you will be expected to do is use a substitution that you're provided with by the examiner and apply it to this integral. Let's see what it looks like. I'm choosing to have x equals sine of u, but there's no problem with using cos. You might want to have a go with cos so that you're doing a similar-ish example, but not identical, to see how well you understand it. But you'll notice that straight away, instead of trying to rearrange, all I do next is differentiate both sides with respect to u. Now you get the same kind of thing if you choose to differentiate implicitly. Differentiate both sides implicitly with respect to x and do a bit of rearranging, you'll get exactly the same result. But I've made it easier for myself by saying I'm going to find dx by du. And on the left, that just gives dx by du. I'm differentiating with respect to u. And on the right, when I differentiate with respect to u, sine u becomes cos u. And that gives me the connection between dx and du. I can write dx as cos u times du. So my integral becomes the square root of 1 minus x squared multiplied by cos u du. Well, so far it seems like we've made life harder. But remember, the reason we chose x equals sine u is that when I do x squared and then take it away from 1 and then square root it, I get cos u. So I'm going to make use of the fact that 1 minus x squared is the same as 1 minus sine squared u, which is cos squared u. And if I square root that, I get cos u. It makes my entire integral look a lot more straightforward. Boils down to integrating cos squared u. Now, even this on its own is not immediately obvious what to do with it. For this, you need to recognize that double angle formulae will come in handy. And it's not an easy one to spot until you build the familiarity with it, because there's nothing in there that jumps out and says, look at me, I'm a double angle formula problem. There's no double angles for a start. But if you're sufficiently familiar with cos 2 theta and sine 2 theta, then you will recognize when you see a cos times a sine, you should be thinking that might have something to do with sine 2 theta. And when you see a cos squared or a sine squared, you should be thinking, I could, if I needed to, rewrite this in terms of cos 2 theta. The nitty-gritty details of whether it's 1 minus that or that minus 1, that you can get when you go back to the formula book and derive the cos double angle formula for yourself. But once you've done it, you can get rid of a cos squared theta and replace it with something involving cos 2 theta. So that's what this next bit is doing. The cos double angle formula, cos 2 theta, can be written as 2 cos squared theta minus 1. Therefore, with a bit of rearrangement, we can find a way of writing cos squared in terms of cos 2 theta, which is something we can integrate. This is what we get. I've pulled the half outside the integral sign to make it a little easier to see what's going on. But although cos squared u cannot be directly integrated, cos 2u is nice and straightforward. We can integrate cos, we get sine, and the 2u is just going to affect the result at the end. We're going to divide by 2 afterwards. Cos 2u therefore becomes a half of sine 2u. If you're ever a bit unsure, just try differentiating your result and see if it gives you back the thing you were trying to integrate. And similarly, 1 integrates to u, and we have half of all of that, and then we add a constant. That we can simplify down a little bit. We get a quarter of sine 2u plus a half of u plus a constant. And don't forget, after all of this work, you still have to go back and rewrite this thing in terms of x. Well, to do that most simply, it's probably going to be helpful to change sine 2u back into something involving sine and cos. So I'm going to make use of the sine 2 theta double angle identity. And then remember, we already know that if x is sine u, then the square root of 1 minus x squared is cos u. So that piece becomes 2x times root 1 minus x squared. And this is our final result. You'll notice we couldn't do very much with u. A half u is going to be a half of inverse sine of x, because that's the only direct connection we have between x and u. Interestingly, therefore, it's not just that trigonometry is required in order to break apart this integral, but the inverse trig function, arcsine, is, if you like, an integral part of the final answer. It's something that has to be there in order to generate this particular result. If you take our answer and differentiate it, you will get the square root of 1 minus x squared. You might remember the results if you looked at the inverse trig results for differentiation. Not necessary for the specification, but they do link nicely to this bit. So if you're curious, you can look back at the optional videos and see how you can differentiate arcsine, arctan, arccos, and so on. Last couple of questions you can have a go at from exercise 11e. This is integration by substitution.